Okay, well, let's do this thing. So, pretty much the two things I'm going to ask you to do, and then I'm going to do this whole bottom part, and I just want you to kind of follow along, take notes, ask questions. But I'm going to ask you to do this LOL, okay, for sure, and then we'll talk about that one. But just the one on the left. Now, let me read through this so we're all on the same page. So, we have two skaters, like skateboarders, of equal mass, and they start from rest at the top of the same hill. They roll down the frictionless surface to the ground, like here and here, on opposite sides of the hill. The skater on the right travels a greater distance along the hill surface than the skater on the left. Ignore air resistance. All right. Now this is just kind of like kind of a heads up, but you don't have to worry about this just yet. The question we're going to answer is how will the velocities of the two skaters compare at the bottom of the hill? So what I want you to do is I want you to draw the LOL for just the guy on the left. Okay, so give that a try. Draw this, and I'll do the thing. I'm going to make you guys big. Give me a signal when you're done with it, and then we'll talk through it. I would expect this will take you a minute or less. So, like I said, give me a signal once you've done that LOL for the skateboarder on the left. Anybody? Give me a signal if you've tried the LOL. Okay, good. Nathan has Emma. Okay, Nolan, Dorian, Charlize. Yeah, okay. I thought probably we just probably okay. That's what I was thinking. You probably had. You just were kind of like chilling. Okay, let me do it now. So, first of all, hopefully you notice it says that they start from rest. That's obviously important because that means for the initial L, there's no kinetic energy. Obviously, they're at the top of the hill, so there's some UG, there's some height. So I always recommend, you can kind of decide how much you want. I think I'm just going to go with 3. I never recommend you just do one uh, unit of energy, but you could do 2 or 3 or 4. Now, let's see. What about the work? Let's see if there's any forces. It says they roll down the frictionless surface. So there's no work done by friction. And it says nothing about them like pedaling or pushing, off while they go. So there's going to be no work done. At the bottom of the hill, well, they're definitely moving, or this guy's moving at the bottom of the hill. And he's got no height. So there's no UG. So if I look at this, I see, conservation of energy means the total energy has to stay the same or be accounted for, I should say. So 0 plus 3 plus 0 equals, this must be 3 then, right? So there's 3 units of kinetic energy at the end. Okay, now, here's what I want you to think about. What I want you to think about is this other guy over here. So this other guy goes down the other side of the hill. Is his LOL going to be different or the same? Now, if you think it's going to be different, then I want you to tell me in what way. So we're going to go into the chat. Everyone go into the chat, private chat me, just send me a chat privately about what you think about the guy on the right. Is the guy on the right, is his LOL going to be the same? If you think it's the same, you just write the same or just same. If you think it's different, I need you to tell me in what way do you think it's going to be different. Now, that could mean like you think he's going to have, it's going to be the same, like it's going to have UG, no K, K, no UG, and empty, but maybe you think it's going to have more UG or less UG, like that is a difference. Okay. So whatever you think, send it in the private chat to me, same or different. And if you think different, tell me in what way. Now, I want everyone to take a guess at this, right? We got 22 people here. So everyone should definitely take a guess at this. How will the LOLs compare? That's really what I'm saying. How will they compare? Will they look the exact same, or there'll be any differences? I got about 10 people, about half of us have made a guess. Take a guess, like that's why we're doing this private. I'm not even going to read these out loud. I'm just kind of like a little survey for me to see what we're thinking. So I'm just looking. But if you don't take a guess, like if you take a guess, it'll really help you after I go over it, or while I go over it, because it'll really help you think about what how close you were. If you get it right, then that's great. If you get it wrong, you can learn from your mistakes. All right, we've pretty much all weighed in. So here we go. Here is the answer. All right, so initially this dude on the right is also at the top of the hill, and as it says here, they both start from rest. Okay, so that means that this dude on the right has no kinetic energy as well. Now, what about his UG? So this is really important, and you probably maybe didn't put a lot of thought into this, but they have the same mass. Now, here's why that's important, because we know this guy's going to have UG. The question is his UG going to be more or less or the same as that guy's? Because our whole thing in LT6 is comparing their energies, comparing the two objects, comparing the LOLs. So will this be like 1 or 2 or 3 or 4? Yeah, really, will it be more or less or the same? And here's how we know. The equation for UG, right, is mgh. Oops, sorry about that. Make this go away. mgh. Well, they've got the same mass, so they got the same m. G is 9.8 on Earth, right? So they got the same gravitational field. And they start from the same height. So they start from the same height, right? So he has the same UG. So you should give them both, whatever amount of UG you gave to the first guy, you got to give the same amount to the second guy. Now, again, as they come down the hill, there's no friction, right? There's no friction. It's frictionless. And neither person is pushing off the ground. So there's no work. And then when we're at the bottom of the hill, well, our height is 0, right? At the bottom of the hill, our height is 0. So there's no UG. So because of conservation of energy, we got 0 plus 3 plus 0 equals, this must also be 3. So it turns out they have the same LOLs, okay? Now, a couple people were talking in the chat about the distance being different. In fact, I do want to give Sela a little compliment here, because she was talking about work. Now, if there had been a force, then they would have different works, because the distance is different, right? And so we know work is equal to force times distance. But because there's no force friction, and because they're not pushing with their feet or anything, there's no work. So this distance doesn't matter. But if there had been friction, then they would have had different works. Okay? Any questions before I go on? So the rest of this, I'm just going to kind of go through on my own. I mean, I want you to take notes and follow along and ask questions, but I'm not going to ask you to make predictions, because this is kind of the new thing to LT6, where it's different from stuff we've done in the past. So here we go. All right, first thing, we got this bullet point here. It says, in order to answer the question above, and sometimes after you do that LOL, you got to go back and remind yourself, what was that question, right? So don't worry if you forgot. I kind of forgot. And the thing is, we want to answer, how will the velocities of the two skaters compare at the bottom of the hill? So we know velocity is all about kinetic energy, right? Motion. So in order to answer that question, we need to compare or look at the kinetic energies at the end, because we want to know at the bottom of the hill, and the bottom of the hill is like the final L's, okay? So that's just kind of like getting you to think about kind of where we're focusing. We're going to talk about things in the order: L initial, O, L final. We're going to talk about it in that order. So what you need to do is you need to compare the two L initials and explain why they're the same or why they're different. In this case, they're the same. So we're going to say both skaters, so both have no kinetic energy, okay, because both start at rest. So remember, the thing we're doing here, the whole thing we're focusing on is comparing the two situations, right? The two objects. And so the first thing we're doing is we're comparing this L to this L, and I'm going to start by comparing the kinetic energies. And they're both 0 because they both start from rest. Now let's compare the UGs, and we're going to say both UGs are the same. Or just say, yeah, both UGs are the same because they have the same mass and start at the same height. Start from the same height. Okay. So now we've completely compared the first L's. All right. Now let's compare the O's, right? So we want to talk about comparing this and this. So what we're going to say is there's no work done because there's no outside forces, right? There's no friction, no pushing, none of that. So there's no work done because there's no outside forces. Right? Just as a little like side note, right? Work equals force times distance. So if there's no force, you know, if that's 0, then the work is 0. It doesn't matter how far you'd go, you know, like 0 times anything is 0. All right. So now we've compared our O's, our L initials and our O's. Now we got to compare the final L's. Okay. And so let's start with the UGs because whatever we identified here is the last thing we want to talk about. And that's why this bullet point is really helpful. It's helpful to help you think about what the last thing you want to talk about. So in this little last L, we're going to talk about the UG first because we know we want to talk about the K last. So what we're going to say is they both have no UG because their height is 0. So both UG equals 0 because they're at the ground. And you know what that means is that the height equals 0. So you don't have to say both those things. Either one is fine. You could say both UG are 0 because height is 0. You could say both UG is 0 because they're at the ground. Now, you'll know you've done this right if the last thing you're going to do is you're going to talk about like the thing from this bullet point, and you're going to start that sentence with this means, right? This means, and you're going to compare those kinetic energies. So this means the kinetic energies are equal. This means the kinetic energies are equal. Now, to understand that, you really have to read the whole thing again, but it makes sense if you read the whole thing, right? Both have no kinetic energy because both start from rest. Both UGs are the same because same mass and same start from the same height. There's no work done because there's no outside forces. Both UGs are 0 because they're at the ground. Well, that means that the kinetic energies are equal, right? It's kind of like saying this. It's kind of like saying 0 plus 3 plus 0, and then if there's a 0 here, must equal 3. Similarly, 0 plus 3 plus 0, if there's a 0 here, must equal 3. All right, so before I go and do the last part, are there any questions on any of this? Okay, let's do that last thing then. Okay, so circle the claim correctly if that answers the question. How will the velocity of the two skaters compare at the bottom of the hill? Okay, here's how I recommend you do this. Do the claim last and make a little like chart, like a comparison chart for each of the guys. So we got the guy on the left and we got the guy on the right. And we got K equals 1/2 mv squared, and k equals 1/2 mv squared. Now, the thing we want to know about the question mark is their velocity. So you're not going to do any, that's our question mark. That's our last thing, okay? So what we're going to do is we're going to this. We want to compare these things. Well, we just said they have the same Ks. So you can circle that to show that they've got the same kinetic energies. 1/2 is 1/2. That's the same. Nothing to do there. And if you remember up here, way at the very top, we were told they have equal masses. So the masses are equal. Well, I mean, if you understand math, which I'm sure you do at this point, you now know that they must have the same velocities, right? If you have the same kinetic energies, the same 1/2, and the same masses, then you must have the same velocity. And now you just have to write that in words. And we can even circle this. We can say they'll have the same speed. So you can say, because they have the same kinetic energy and the same mass, they must have the same velocity. Because they have the same kinetic energy and the same mass, they must have the same velocity. There you go. All right, folks, any questions on anything I just did in this example? I went through it slowly because it's brand new. It's our first real look at LT6, but that doesn't mean you don't